All right, this is assignment 6-1. So let's start here. This is the second fundamental thermocalculus, or part 2. We're going to practice it together. So let's write down question number 1. Understanding the derivative and the integration undo each other, but it's when there's algebra in the bound or the limit that we have to be a little bit careful. It can be really simple if you let it be really simple. So here it is. If you have and you take the derivative with integration, they undo each other, right? Like if you integrate and then take the derivative, it takes you back to where we started. But if we have algebra, then we substitute the algebra limit in for t. So any constant to whatever the algebra is, it's just a substitution question. For number 1, the answer is just x squared subtract x plus 1. Done. So all you do is any constant to x, replace every t with x, and it's done. Here, any constant to x, take out the variable t, put in x, and you have your answer. That's the cube root of x squared minus 5x. Done. Number 3. See how simple it can be? Any constant to a variable. So it's just a substitution question. So just substitute in. Where there's an x, put in t. Pretty simple, right? 2 over t, subtract 5. Number 4. What I'm looking for again is the bottom bound, a constant. Any constant. So 0 to 2t, just a substitution question. So put in 2t for x, and you get sine 2t. Done. Number 5. Oh, and there's one part left here I didn't quite do. For this one, when you substitute in, you also have to take the derivative of the bound or the limit, and that's a hook. So in this case, the derivative of 2t is 2, and you need that hook that gets created from the bound. So let me show you so far. So number 1, the derivative of x has no hook, has no hook, has no hook. So the first 3 questions you just plug in. But for number 4, when you plug in 2t, the derivative of 2t is 2, so it creates that extra hook. That's it. Number 5. Again, look and be careful. Now, for this one, the bottom bound is x and the top is a constant. So we have to be careful here. So you're going to plug in the top bound first. So when you plug in 3 and take the derivative of any constant is 0. But we have to start with 0 and then subtract, then plug in x. And know that there's no hook here because the derivative of x is 1. So this is what it would look like. So because the bounds, we have a constant, so the derivative of a constant is 0, but the order matters when you subtract. So it's 0, subtract, and then plug in. If you like, all of these would look like that, right? Like the order matters. When you take the derivative of a constant, it would be subtract 0. So if it makes you more comfortable, we can do that. Here, the order got flipped. So the 0 was first, and then subtract that. But that matters because when you subtract, it's going to have that negative in front. Number 6. Again, notice the order. So the constant is in the numerator. So that means I'm going to start with 0, subtract, and then I'm going to substitute in. So it's 1 subtract x squared to the exponent 4. And then the derivative of x squared is 2x. And you remember that hook. 0, subtract, do that substitution. The derivative of x squared is 2x, and it's done. Number 7. Again, notice here I have both bounds are algebra. So we start with the top bound. So plug in 4t for x, and then it has the hook 4. So the derivative of 4t is 4. subtract. Now plug in 3t for x, and the derivative of 3t is 3. Done. This is what it looks like. Substitute, and then the derivative is the hook. Substitute, the derivative is the hook. Notice it's top bound, subtract, bottom bound. 8. In number 8, again, be careful. Here we have the bottom, subtract the top. So it goes from 1 to A. Now, what makes this one different? Number 8. Do you see a derivative in front of number 8? This is not the fundamental rule of calculus part 2. So number 8 is different. Notice there is no derivative in front, so it's different. You have to know how to integrate. So let's do that. So for number 8, I'll show you. Integrate from 1 to A. So you just have a variable you use. And we're going to go through the steps. It's the anti-chain rule. So that's what makes number 8 different. That's why it says be careful. All right. So how do I do this? There's no derivative in front. So I need to integrate. So step 1 is the hook. Before I can unhook it, the hook has to be correct. The derivative of the base is 6t. That's the correct hook that I'm going to unhook. Before it was 1, so the fraction I need is 1/6. And then I can circle the hook and unhook it. So it's 1/6, and it's 3t. Now add 1 to the exponent. Divide. And we're going from 1 to A. So that's like 36. So it's like 1 over 36. Plug in A to begin with. Subtract. Rewrite it again. This time plug in 1. You don't have to simplify it. And it's over. So you first plug in the upper bound. Subtract. Plug in the lower bound. And that's a great answer. Number 9. All right, I like these questions. So these are story questions again. So whenever stories come out and you have to interpret a graph, they can be simple if you let it be simple. So I'm going to read it for you. The graph at the right represents the rate of flow of irrigation water from a reservoir during a 24-hour period. So the graph is a rate. That means it's a derivative graph. So if you're looking at a rate, that's a derivative. It says write a sentence telling what point A represents. All right, I see point A. It's a rate. So to write a sentence means I involve both axes. So in other words, what is 8? That's time in hours. At midnight is 0. So that's 8 a.m. So we're going to write down at 8 a.m. Well, what's happening at 8 a.m.? Well, the story is about irrigation water. So irrigation water is flowing at what rate? At a rate of, and at A it's what, 1? So it's 1,000 gallons per hour. It's just a matter of whether you can interpret the graph that's in front of you. And again, it can be simple if you want it to be simple. So here's my sentence again. So interpret point A. So I have to mention both axes. So the x-axis is time. So at what time? And then the other axis represents the rate. And what's the story about? So at 8 a.m., irrigation water is flowing at a rate of 1,000 gallons per hour. And you could say flowing from a reservoir. 9b, find the area of the shaded part. So when I look at the shaded part, you could break this down into different shapes. It's up to you how you want to do it. I see a big rectangle in the middle. Just be careful of the units. So the height of this rectangle is 3,000. Can you be careful about that? So what's the height? So I'm going to do a rectangle here. The height is 3,000. And the width of it is hours. How many hours is the width? It goes from 10 to 16. That's 6. So 3,000 times 6 That's 18,000. And then I'm going to find the area of one square here, a rectangle. That's 1,000 times 2. So the height of that rectangle is 1,000, and the width is 2. So that's 2,000. And then a triangle here. Do you see that triangle? So that's half the base times the height. So the height of that triangle is 2,000. And the base of that triangle is 2. So 1/2 of 2,000 is 1,000 times 2 is 2,000. And then I'm going to add it all up. So I get 22,000. And then show your computations, which I did. So there's the rectangle, there's the big rectangle, the small rectangle, and the triangle. Add it all up, and you get 22,000. And when you integrate a rate, then the unit is the answer. So the rate was gallons per whatever it is. What is it? Gallons per hour. But when you integrate, it's no longer a rate. It's whatever the unit is, which is gallons. So when you integrate that, the answer is 22,000 gallons. Part C says, write a sentence telling what the shaded area represents. So again, both axes. So what's the time? From 8 a.m. to, that's noon, that's what, 4 p.m., right? 4 hours after noon. So from 8 a.m. to 4 p.m. So start there. Nice and simple. Let it be simple. From 8 a.m. to 4 p.m., how many gallons of water flowed out of the reservoir? 22,000 gallons of water flowed from the reservoir. So what makes this a good sentence? I'll show it to you. So a good sentence in calculus involves both axes. So it involves the axes about time and my answer, which is the other axis. So from 8 a.m. to 4 p.m., 22,000 gallons of water flowed from the reservoir. So it's not just the answer 22,000, but it's within the context of the question and the story as well. Part D. Set up an integral which represents the total amount of water released during the day shown. So during the day shown would be from 0 to 24, and you're integrating W. All right, this is what it would look like. So you're integrating, so from 0 to 24, you're integrating the rate from 0 to 24 hours. This will represent the total amount of water that's been released. And I think in part E, you have to find it. Oops. Right? Find the value of it. So just find the value of the integration, which is the entire area under the curve. So now we already found the shaded area. I'm writing that down. That's 22,000. Plus, okay, what's this triangle here? I need to add it to it. So the base is 4 times 1,000. And it's 1/2 the base. So half the base times 1,000. And we have a triangle over here. It's 1/2. Now what's the base over here? 16 to 22. That's 6. And then the height of that triangle is 3,000. Let me show you. So we already found this, and then the triangle on the left, the triangle on the right. So let's put it together. That's 2,000. That's 9,000. Half of 6 is 3 times 3. And this is what? 1133. And it doesn't ask us to write a sentence, so it's just 33,000 gallons. All right, that was question number 9. Number 10. Another graph, another story. I just want you to enjoy the stories in calculus when they come up. The graph at the right represents the birth rate. Do you see that word rate? So when I see the word rate, it means it's a derivative graph. I might sneeze in a second. Sorry. All right, there we go. Did you say bless you? So it's a derivative graph, so I need to be aware of that when I look at it. So it says, tell what point A represents. Where's point A? Okay, so let's look at the first axis. 2 is time in years, and 0 is 1990. So A would be 1992. So in 1992, that's a good way to start the sentence. So in 1992, and really you should say at the beginning of 1992, because 1993, like all of this is 1992. So at the beginning of 1992, so at the beginning of 1992, what happened? What's the story about? So the story is about the birth rate in a Utah city. So the birth rate in a Utah city is, and what's the rate? It's thousands. So it's 3,000 births per year. So at the beginning of 1992, the birth rate in a Utah city is 3,000 births per year. It doesn't have to be complicated. Part B. Approximate the integration using geometric shapes from 2 to 6. So from 2 to 6, what geometric shape would you use to find the area here? So from 2 to 6 to begin with, do you see a rectangle that's like 2 rows? So from 2 to 6, the width of that rectangle is 4, and then the height is going to be 2,000. So from 4 times 2,000, that's 8,000. And then I see like a triangle here. So just approximate what that triangle would be. The base of the triangle is 4, and the height of that triangle is 1,000. And then I see a triangle here on the other side to approximate to 6, and the base of that one is 2. And the height of the triangle here at 6, I see from here to here is 2,000, the height of that triangle. It's like putting together a jigsaw puzzle. And then part C says, what does that mean? So when I put it together, the approximate area I got was 12,000. And then what does that mean? Well, what it means is when we integrate from, what was it again, from 2 to 6? Yeah. So when I integrate from 2 to 6, b at t dt, and we say the approximate answer is 12,000, what that means is from what year to what year? From the beginning of 1992 to the beginning of 1996, approximately, there were approximately how many births? 12,000 births in one Utah city or a Utah city. Let me show it to you. So it doesn't have to be complicated, but it needs to not be missing any information. All right. So from the beginning of 1992 to the beginning of 1996, there were approximately 12,000 births in a Utah city. So when you integrate a rate, it's whatever the unit is. So births per year just becomes births. So how many births were there approximately over that 4 years? And there was approximately 12,000 births. See, it doesn't have to be complicated. We can work at it together. When was the birth rate the lowest, and what was the birth rate at that time? So what was the lowest part of the graph? So it looks like at 1990 and 1994. So at the beginning of 1990 and 1994, the birth rate was the lowest at, what was the birth rate? 2,000 births per year. Let me show you my sentence again. So at the beginning of 1990 and 1994, the birth rate was the lowest at 2,000 births per year. Can you be comfortable interpreting a rate graph or a graph and comfortable writing a good sentence, but not a complicated sentence? All right. Moving on. 11. This is how you get stronger, by practicing together. Number 11, the graph at the right represents the density of hikers on trail. Means how many hikers there are in an area. That's what, not like how thick a hiker is, but like how many hikers are in an area. You knew that, right? Okay. Tell what point A represents. Okay. So hikers per mile is a rate. So A, first of all, what's 3? Distance from a trailhead. So 3 miles away. So I'm going to write down 3 miles away from the trailhead. The density of hikers is, what is it, 30. And it's not, that's the number, 30. And it's 30 hikers per mile. So 3 miles away from the trailhead, the density of hikers is 30 hikers per mile. Part B. Can you integrate? No, it tells you. From 0 to 3, the answer is 110. So from 0 to 3, the answer is 110. Write a sentence with numbers and units stating what it represents. So 0 to 3 means, what's a good sentence to start with? From 0 to 3 miles away from the trailhead, so from 0 to 3 miles away from the trailhead, what does that represent? There are 110 hikers on the trail. So from 0 to 3 miles away from the trailhead, there are 110 hikers on the trail. Remember again, the rate was hikers per mile. So when you integrate, it's just what the unit is, which in this case is hikers. Part C. I hope this is getting easier for you. Use the derivative at 3 equals negative 6. Use local linearization to approximate the density of hikers 3.1 miles from the trailhead. So local linearization means I need a tangent line. So for a tangent line, I need a point. So at 3, the point is 30. So I need 3 and 30, and the derivative is given. The derivative is negative 6. So in other words, your x is 3, your x is 3, your y is 30, and you're given the derivative. So the slope is -6. It gives you the slope. So the equation of the tangent line would be -6, x subtract 3 plus 30. So this is what it would look like. So 3 and 30, that's x and y. The slope is given, -6. And then plug in 3.1 for your answer. So that's 0.1. So what's 30 take away 0.6? So think of money again. So that'd be 29.4, right? Double checking. And then that's hikers per mile. So if you wrote a sentence, 3.1 miles away from the trailhead, the density of hikers is approximately, 29.4 hikers per mile. So 3.1 miles away from the trailhead, the density of hikers is approximately 29.4 hikers per mile. When it's a rate, it's okay that it's in decimals. All right, next. Another story, number 12. This is how we get stronger. To the graph at the right represents velocity, miles per hour, a rate. Tell what point A represents. All right, you tell me. Can you figure that out? Press pause, then press play. A. So, hours, afternoon. So we're going to start at 1 p.m. Okay? So at 1 p.m., what happening? So the velocity is what? 20 miles per hour. So at 1 p.m., the velocity is 20 miles per hour. Part B says, tell what the slope between B and C represents. So slope is derivative, and the derivative of velocity is acceleration. So what does the slope between represent? It represents the acceleration. So, again, the time, so between 4 p.m. and 5 p.m., and what is the slope there? So between 4 p.m. and 5 p.m., the acceleration was, what's the slope? How many up? So up 20 and over 1. So it'd be 20 miles per hour squared. That's how you write down acceleration. So between 4 p.m. and 5 p.m., the acceleration was 20 miles per hour squared. Or you could write it 20 miles per hour per hour. That's another way to write acceleration. Part C. What is the velocity at 12:15? So at 12:15, we're in the middle of this segment here, right? From 0 to 1, 12:15. Now, I'm not going to just go, it kind of looks like. I need to know the equation of that line to be able to answer that. What's the equation of that line? So, the velocity of that line, the slope is 20. So it's 20x. 20t. So we're using t. So the slope is 20, the y-intercept 0, so it's 20t. So that segment, 20t, because the slope is 20, and it's mx plus b, and b is 0. And then at 12:15, we got to plug in what that means. So that's a quarter of an hour. So 12 times 0.25, or 20 times 0.25, 2 times 25, that's just, what is that? That's just 5. Double 25, that's just 5. So the answer is 5 miles per hour at 12:15. What was the next one? How about at 5 p.m.? Do you see at 5 p.m.? It's right there. That's 40. You don't have to do anything fancy for that one. So it's right. If you have the answer, great. If it's in the middle of a slanted line, you have to find the equation of that line and then plug in. But this one's just there. It's 40. What is the acceleration at 12:30? So 12:30 is here, and the acceleration is the slope there. So at 12:30, from 0 to 1 p.m., the acceleration doesn't change. It's a constant slope, up 20 and over 1, so it's 20 miles. So again, what time is it? At 12:30, the acceleration is, again, the slope. So it's 20 miles per hour squared. And then what was the other one? At 2 p.m. So at 2 p.m., it's flat. The slope of a horizontal line, the acceleration 0. So it's still moving forward, but it's not accelerating. So at 2 p.m., the acceleration is 0 miles per hour squared. So there's none because it's just a flat line. So at 12:30 p.m., the slope of the line at 12:30 is 20, and the slope of the line at 2 p.m. is 0. What is the distance traveled from noon to 5 p.m.? And to find the distance traveled, how many miles? You find the area under the curve. So let's just break it down. I look at and I see a triangle. Half the base, the height is 20. I'm just going to break it down into shapes. Rectangle, 1 to 4, that's 3 times 20. I see a rectangle again. I should have done a longer rectangle. Whatever. 1 times 20. So I see 1 and 20. And then I see a triangle here. And it's 1 again and 20. So half the base times the height. And then I put it together. And let's see what I get. I'll show you my work. I get 80, 90. I get 100. So there's no story involved, so I'm just going to write down 100 miles. So the first triangle is 10, a rectangle 60, another rectangle 20, half the base times the height, the last triangle 10, added up, and the total distance traveled is 100 miles, not a rate when you integrate or find the area. All right, number 13. This will be the last one for this video. So the graph at the right represents acceleration. All right, be careful here. What is the acceleration at 2 seconds? So at 2 seconds, it's in the middle of a line segment, so I got to find the formula for that line. So 0, what's the slope? Up 10 over 3. So it'd be up 10 over 3 plus 0. So it's just 10 over 3t. That's what acceleration is. So up 10 over 3, that's the slope. The y-intercept 0, where it started at. And then it said, at what time? At 2 seconds. So plug in 2. And you get 20 over 3 feet per second squared. Just double checking the answer key. Yep. So first, find the equation of that line, slope, y-intercept. Then plug in 2 into that equation, and you get 20 over 3, and those are the units. Part B. When is the acceleration 10? So look at 10 and look across on the graph from 3 to 4. So from 3 to 4 seconds, the acceleration is 10 feet per second squared. Units are so important. Don't be sloppy with your units. So from 3 to 4 seconds, the acceleration is 10 feet per second squared. C. In part C, what is the minimum acceleration? Way down here, right? -5 feet per second squared. So you're slowing down. D. If the initial velocity is 0, what is the velocity at 6 seconds? So if the initial velocity is 0, then we integrate from 0 to 6. You integrate the acceleration. So we're going to start at 0 and then add the areas that I see. So that's a triangle. Can you find the area from 0 to 6? So half the base times the height. That's 3 times 10. A rectangle, that's 1 times 10. And then another triangle, half of 2 times 10. So if I put that together, half of 30, 10, half of 20, I get 35, and it's 35 feet per second. So the velocity at 6, I get 35 feet per second. Making sure that's right. Yep. Here's what it looks like again. So the initial was 0, and then we integrate acceleration and add it to 0 to know what it is at 6. So from 0 to 6, integrate the area under the curve, and you get 35 feet per second. E. If the initial velocity is 20, what is the velocity at 6? So then you just go 20 plus 35, and you get 55 feet per second. Make sure it's that simple. Yep. And then F, if the initial velocity is 20, what's the velocity at 7 seconds? Well, already up to 6, we know it's 55, and then you just integrate from 6 to 7. Now be careful, because from 6 to 7, it's negative. So what's this triangle? The base is 1 and -5. So if I put that together, it's going to be subtracting because you're slowing down. So half of 15 is 7.5. So 55 take away 7.5. So 52.5. No, 55 take away. Oh no, that's not 15, that's 5. That's 2.5. Ha. So it's 52.5 feet per second. Let me show you my work. So I said if the initial was 20 and not 0, you just go 20 plus 35, and that's what it would be. And then at 7, we already know at 6, it's 55. So integrate from 6 to 7, find the area, and it's negative, so we slow down, and that gives you the velocity. Again, practicing, not giving up, being confident, getting stronger, interpreting graphs. All right, Mr. G Math over and out. Until next time, we'll do part 2.